behalf of IPT, on behalf of IPT Mumbai Sub-Regional Council, I welcome you all for the inaugural function of the lecture series we have arranged in the memory of our beloved Professor R.M. Dharkar. To start with, I invite Professor Bole, Secretary of Mumbai Sub-Regional Council of IPT, to give us a brief idea of IPT and the activities of Mumbai Sub-Regional Council. Professor Bole.
Thank you, Madam. The Indian Association of Physics Teachers, shortly it is called IAPT, is a grassroots organization working for the upgradation of physics teaching as well as the physics teachers by conducting various programs and activities. And these activities are conducted throughout the country.
We can't hear you.
So,
could you be louder, sir?
1 minute. Hello.
Sir, little louder, please, if you can.
Okay. I'll try. Yes, okay. The IAPT was established in 1984 by Professor Khandelwal and other physics teachers. And as on today, there are more than 20 regional councils, including the sub-regional councils for administrative purpose, which are formed throughout the country. It has a live membership of more than 10,000 physics teachers, physics students, and some of them are from foreign countries also. It also conducts examinations, particularly called as NSEP and NGPE, which are conducted. NSEP is conducted even for other subjects, that is chemistry, biology, astrophysics, and for junior science. But the NGPE is also conducted for the undergraduate students particularly, and these exams are conducted every year on regular basis without any break. It conducts additional competitions, and these competitions are NCIEP, which is the National Competition in Innovative Experiments in Physics, as well as NCEWP, which is the National Competition for Essay Writing in Physics, and NCICP, which is mainly related to the competition, related to the computational physics. And in all these competitions, the students, undergraduate students, junior college students, as well as the teachers can participate. It also organizes many symposia and activities based on learning programs like NSSP, which is a National Student Symposia of Physics and on Physics, and Anveshika, which is also labeled as NANI, which is a short form of National Anveshika Network of India. And these particular programs are conducted every year without any break. Regularly, it also regularly publishes the bulletin, which is also called as a Physics IAPT Physics Bulletin. And now the e-version of this bulletin is made available. This bulletin is available free of charge to all the live members, and e-version is available to anybody who is visiting the website of IAPT. It also publishes another journal based on related to or devoted to physics education, and it's this particular organization and its work is purely voluntary. That means there is no question of asking remuneration and so on. But I have seen the people from renowned physics research laboratories, renowned scientists, at the same time the very, very popular institutions which are the members of this organization, and they contribute for the development and betterment of physics education. Friends, as this particular sub-regional council, Mumbai 08B, had one meeting in December, and that time we discussed what can be done for the next year's program. And we realized, because that time it was just a few days were passed, and we were having one meeting discussing the contribution of Professor R.M. Dharkar also. And through that, the idea came into our mind that let us have a R.D. Dharkar, Professor R.D. Dharkar Memorial Lecture Series, and under that series we'll be calling various people from physics background, and this particular idea was supported by almost all the members of this sub-regional council, because Professor Dharkar worked almost for 40 years for IAPT, and his main contribution was related to examination. Although I say examination, his contribution in other areas are also pronounced. He was a very devoted and loving person, and was available to any particular physics teachers in Mumbai region, particularly. And I have experienced this in my teaching life. The students were also very much were accepting his knowledge and guidance. He was serving at Wilson College, Mumbai, and that is why this particular regional council thought that let us have this series every year. 2 lectures will be organizing, and that will benefit the physics community. That was the basic idea. And with this basic idea, rather than taking much more time, I will hand over the mic to the next speaker. Thank you.
Thank you, Bole sir. Today we have with us Professor Pradhan, who was the president of IAPT for many years. He has retired as a director of HBCSE TIFR few years back. He has worked with Professor Dharkar for many years, and so was closely associated with him. I would now request Professor Pradhan to tell us about Professor Dharkar and his work on various fields, especially on the platform of IAPT. Professor Pradhan.
Thank you, Shamla. It's a pleasure. It's a pleasure to be with all of you, especially the members of the IAPT Sub-Regional Council of Mumbai, which was close to me and also close to Professor Dharkar. And it's a great occasion to sort of speak to my colleagues from Mumbai about Professor Dharkar. Okay, let me just see if I can really do justice to his personality, because Professor Dharkar was a multifaceted personality, and he did lots of things. I mean, teaching, and of course, participating in all the national standard examinations in physics. And he was the founder of many new concepts as far as IAPT was concerned. He was an extremely good teacher. He was a very, very good and effective coordinator of the national examinations that IAPT conducted. And he was a great colleague also. So let me begin. Okay, let me say what his great qualities were. First of all, in my opinion, Professor Dharkar was a very, very good teacher, an excellent teacher. In fact, what I would say is that he was a teacher in the classical mold. Let me explain what I mean by that. When I was a student, say in the early 60s, of BSc, MSc, and so on, of physics at a university like Mumbai, we used to have teachers whom I would say, who in my opinion were the classical mold teachers. That means they knew their subject very well. They loved the subject very well. They loved the students very well. They were at times strict if necessary, and they got things done from the students, and they got students interested in the subject. So in that sense, it's a mixture of sort of, a loving nature as well as a disciplinary nature, and the strength of the knowledge of the subject. All these 3 things, I think, were very, very saliently seen in Professor Dharkar's personality, and that's why I call him a teacher in the classical mold. Fortunately, for me, even my school teachers and later on my teachers at the university as well as in my college, were of the same mold. And therefore, I consider myself to be very lucky. And whatever I could do, I mean, later on, okay, in terms of some kind of, teaching and also work in terms of research in physics, research in physics education, and so on, I owe it to my teachers and colleagues like Professor Dharkar. Professor Dharkar, besides being a good teacher, okay, he was a meticulous worker, a very, very meticulous worker. He took up the work of Mumbai regional, Mumbai sub-regional IPT Council way back in the 90s, early 90s, 1993, 94, with Professor Umadikar. And they both were really so devoted to the idea of IPT. And they used to go from college to college, inspiring the teachers and so on. And I remember having attended several meetings, okay, either at the Wilson College, where Professor Dharkar taught, or either at the Institute or at the Institute of Science, where Professor Umdikar taught. So I think, both these teachers were great teachers, and their love was demonstrations. Especially Professor Dharkar's laboratory was full of all demonstration apparatus. And I think he used to take pride in showing demonstrations to students. And I think, unfortunately, I must say that we must revive that, because that's a kind of vanishing species now that has come up. And we must remember, ultimately, physics is an empirical science. And all empirical sciences, ultimately the validity of all the empirical sciences is in observations, in experiments, in demonstrations, and so on. And therefore, if we don't have this component in our teaching, then I don't think, we are carrying the subject to the students and so on. So we should really take care of that. Professor Dharkar, in my opinion, was really a very good experimental hand, and he made use of experiments and observations and all kinds of empirical evidence in his teaching also. And that really became evident even when he was associated with the Olympiad programs, because he was the he was the principal figure in conducting the practical sessions for the Olympiads. And as you know, what happens, the Olympiad students that we get, and especially we need to train them, because we needed to train them not just for theory. In theory, they were all good, because they really tried to prepare for the IIT and other examinations and so on. But at the same time, I think we found that they were not adequate in experiments. And that's why what I felt was this, that we needed some very good guidance for these students. And Professor Dharkar, Professor Desai, Professor Ugalapurkar, these were the teachers who really took on their shoulders the responsibility of demonstrating experiments, get experiments done from the students. And that's how, once that was well established, we really got good results for international Olympiads and so on. So in that sense also, we must continue the tradition of demonstration of experiments, even for the best of the students. We should not expect them to do well automatically because they are likely to do well in theory. Another very important aspect of Professor Dharkar's personality was he was a very, very important and inspiring senior colleague for all of us, because he was the person who really made me realize that I should take up IPT work. And not only that, but he more or less persuaded me to take up the the presidentship of IPT. And at every stage, whenever I required his help, I approached him, and he was always ready to help. And he not only helped me, but he helped everybody who needed help. And that's how I remember. And I really miss him. The fact is that even though, of course, it has been more than how much time, I don't remember. He was born in 1936. He was 84 when he expired, and that was in December 2020. So it's more than 2 years that he expired, and I still miss him. Because I feel like, just taking up the phone and calling him and, having a chat with him. Because chatting with him was always so nice, so invigorating and inspiring. And therefore, like most of you, I miss him very much. And I must say that. What were his contributions to IPT? His contributions to IPT were multifold. One was, he was one of the founder members of IPT. Along with Professor Khandelwal and Professor Kapoor, he was one of the founder members of IPT. And from that point of view, I think he was one of the members of IPT who really sort of, not only founded IPT, but founded also the culture of IPT. For example, in IPT, a simple cultural fact is that in IPT, we do all voluntary work. We are devoted to physics, but we do physics work of teaching and demonstration and so on, without, any compensation in our mind whatsoever. So the idea of taking no remuneration or any work, our work is entirely voluntary. That tradition was established by these great stalwarts of IPT, and certainly Professor Dharkar was one of them. His work for various committees of IPT, like even the finance committee and so on, was always so important. It was so well sought after. In fact, I used to always go to him, and without his advice, we would not be able to sort of take very important decisions. He was one of the best coordinators we ever had for the National Students Examination in Physics. He was also the person who really, in a sense, started NSAP, carried it on his shoulders through many years and so on. And then in that process, he built up a lot of younger people. I think what was his contribution was to also prepare younger members of IPT for taking up the responsibility of IPT. And in that sense, I feel that his contribution as founder of NSCP, and also somebody who really continued with it, and then bearing the standards. I think what was important was really, he was so meticulous about all the questions, especially in theory and so on. And he was so meticulous, especially whenever he examined students in experiment and so on, that he set an example for all others and so on. So in that sense, as I said, one of his contributions, though of course not direct, it was indirect, and that was establishing a certain standard of work at IPT, certain standard for IPT culture. And I think that is something that I would really sort of, miss him for. He was an advisor for all aspects of IPT, advisor par excellence. And I would say that, for especially the experimental part of our IPT program, including the Olympiads and so on, his contribution was very important. And I believe that, all of us need to go by his sort of, way of going about in demonstrating and putting up, our work. Finally, I'd just say this, that experiments are as important as theory for learning physics. And I think Professor Dharkar knew this. And I think he tried to see that this really happens. And not only Professor Dharkar, but a number of other members of IPT, the IPT senior members, like we had Professor Saraf, we had Professor Khandelwal, we had Professor Umdikar, we had Professor Samanto. All these people, they really have been singular-minded in emphasizing the importance of experiments in physics. And I do believe that they were right. And I do believe that if we go by that, we should certainly make physics more interesting to our students. And not only that, but we'll raise the standard of teaching physics in our country. And that's the call of IPT. And I think we all should really go to that. So please, remember this, my colleagues, my request to you. And I think we all, with especially Professor Ahluwalia at the helm of the affairs, I'm so happy that he is now the president of our organization, is already worked out a great program for us for the next few years and so on. And we should really all follow up that program. And if we do that, we shall make IPT a dream organization. Not only a dream organization, but what we'll do is that the cause of physics education in the country, that should really be continued. And I think IPT is one of the major functions of IPT is really that. And therefore, I would say that this is a kind of pledge that we should all have. And let me honestly once again appeal to you under Professor Ahluwalia's leadership, and of course with Rekha's general secretaryship, and all of you, especially in Mumbai and in number of other regional councils, if we all take it up as our task and our pledge, we shall be able to make India very good in physics. And I think that's the call of the hour, because national education policy, new policy which has come up, essentially emphasizes good science teaching, and good science teaching includes mainly good physics teaching. By and large, physics teaching is considered not very easy anywhere in the world, but I think we should really take it up very seriously. If you need any help from me, I'm always there. And I think most of you have been my past students. And therefore, once again, I shall emphasize that I trust my students, and with the help of my students, we shall be able to do well. Thank you once again. And I pay my humble tribute once again to Professor Dharkar, to his memory. And I must say that I really miss him. And we shall all try to sort of, basically follow the method, follow his advice as far as physics teaching and physics demonstrations are concerned. Thank you.
Thank you, Professor Pradhan. Let us now come to the first lecture of our series, which will be delivered by Professor P.K. Joshi of Bhabha Center. I would request Mahesh Shetty sir to introduce Professor Joshi to the audience. Mahesh sir.
Hello, am I audible?
Yes, you are.
Yeah. So good afternoon, everyone. On this platform of IIPT and the very first lecture of Professor R.M. Dharkar. Because he was, as Professor Pradhan mentioned, Professor Dharkar was more interested in experimental teaching, that experiments are a very important and essential part of science learning. We have decided that this particular series will mainly focus on education, and in the very first series, we have got Dr. P.K. Joshi from Homi Bhabha Center for Science Education, which is under TIFR. He is faculty there. He had done MSc in Physics 1988 from IIT Bombay. Later, he completed his PhD in Experimental Nuclear Physics in 1994 at Louisiana State University. Currently, he is president of IJSO, that is International Junior Science Olympiad. He is vice chairman of BASE, that is Bombay Association for Science Education, which mainly conducts various kind of sessions for the school teachers. He is member of Board of Governors for IIT Bombay, member of Management Council, SNDT Women's University, Mumbai, and he then also involved in developing school science experiments and conducting teacher training programs based on those experiments. So, very good afternoon, P.K. Joshi sir. The platform is with you.
Okay. Thank you, Mahesh. I just have one question. I had difficulty in hearing the previous talks. Am I clear?
Yes, sir, we can hear you.
Okay, fine. Thank you. Okay, so let me share my PPT. Okay, I'm thankful to the organizers. It's a pleasure in one sense to be doing the Professor Dharkar's memory lecture. I had very little association with him, but whatever little I had was very pleasant and very fruitful. And it also feels appropriate that when I chose the topic, I probably did not realize, but this is the most appropriate topic because it's going to deal with how we can refine our experiments. Besides just telling about the program that I'm going to talk about, it's also useful not only in nuclear physics, but it will also be useful to people in other branches of physics when they head towards a research program or even doing experiments, how to take care of issues which should not be there. That's of course a small portion, but nevertheless it will help the students to refine the experiments and the publications. This topic, nuclear data evaluation, is something which is not very well known. I will be glad if people are aware about this program. But unfortunately, at least outside Mumbai, not very many people know about this program. So I thought I will also introduce this program, experimental program, to the teaching community. So what's the program today? We'll talk about, begin with what is a nucleus, the stability of a nucleus, what are the types of radiations, and then what is the importance of gamma energy? It's especially the measurement of gamma energy and related issues. What are the problems faced in published data? Now, this is not restricted only to India, but we also face these problems across the world. So there is nothing particularly bad about India. Role of data evaluation. So what is this program and what this data evaluation does? Process of the data evaluation and what are its offshoots. Also, I will discuss why we need this and with some brief history. My observations, my experience with this program for the last 10 years and what it has resulted. So let me begin with the starting point where everybody feels very common, that the most simplest of the atom is the hydrogen atom with a proton and an electron. It's a stable nucleus, stable atom. So is the deuteron, where you get a neutron along with a proton. Now the story begins to change. If I get another neutron, we get a tritium with a half-life of 12.3 years. 1 second, I just need to change my view. Okay. So if you add, so of course it will convert a neutron into a proton because the nuclear force is so strong that if it doesn't like this combination, it cannot get rid of a nucleon. So it converts from a neutron to a proton, and to balance it, it emits out the electron from within the nucleus called as the beta particle. If you have a combination of 4, and now we drop the electrons out because they don't play any role, it is the most stable and very strongly bound combination. It is so strong that if I add a 5th particle, which is a neutron, it is kicked out within 10⁻⁻22 seconds. Same is the story with a proton. So whether it's 5 helium, 5 lithium, they both have a very strong, a very small half-life of the order of 10⁻⁻22 seconds. And so in nature, there is no stable combination of mass 5. Same is the story with mass 8. If you make 4 and 4, it is an extremely unstable combination and it immediately splits into 2 heliums. If you make 6, then it's a stable combination. If you have 7, if you have 9, they are stable combinations. So what you realize is that n equal to z is a stable combination up to z equal to 20. At this point, what happens is that the Coulomb interaction between the protons is repulsive and it starts beginning to get stronger. And so protons want a little more space to adjust the repulsive force, but space is not permitted within the nucleus. So this gap or space is filled by extra neutrons. And what you can see is that in this chart where black dots are the stability, the highest n equal to z is at 20, 20. 20 protons, 20 neutrons. And then you need larger and larger number of neutrons to make it stable. All nuclei which are to the right of this black line have extra neutrons. And so it's an unstable combination where it will convert the neutron into proton, giving a beta particle. If you have nuclei which are on the left side of this dark line, it has deficiency of neutrons. And my word, I'm saying deficiency of neutrons and not excess of protons, because we talk in terms of isotope with Z, which is same. So here there are more neutrons, on the left side there are less neutrons. So since there are less neutrons, protons are converted to neutron and they approach the stability line, giving out a positron. If the mass is heavier, somewhere around 100 and above, alpha decay becomes possible. And where nucleus jumps towards the stability line, giving out combination of 4 nucleons. Okay. And so the journey towards the stability line is faster. When you go to mass 200 and above that, the nuclei is even more kind of impatient and doesn't wait for alpha particles to be emitted. It simply splits into 2, giving out 2 products which are somewhere halfway in the chain, thus having excessive neutrons and excessive energy, and hence they release the energy of neutrons, and this is the fission process. So we have now seen the source of radiation for beta, positron, neutrons, and the alpha particles. Of course, at the edge, the nuclei can simply kick out a neutron or a proton. So even the proton emitter is available at the edge of this chain. With all these combinations, what we are left with usually a residual nuclei which has residual energy. So current nuclei decaying to the daughter nuclei with any of these beta or alpha or fission tracks lands up with a nucleus with residual energy. And that residual energy is emitted by gamma energy. And hence you can see that of all the radiations, gamma is the radiation which trails any of the other radiations. And hence it's a very important window to study the interactions between protons and neutrons inside a given nucleus. And that's the importance for gamma energy. It is a window, and all the nuclear structure physics information is obtained from studying the gamma energy. Just for the record, nature is not very symmetric in this sense, that out of 3,300 nuclei, 300 are stable. Only 164 are Z and N even combination, about 100 with odd even combination, and only 4 odd N odd Z combinations are stable. But this is just for the record. So with this important study, to study the nuclear physics, structure physics, the gamma energy is a very critical study. And this is just a single picture to explain all the radiation. Once we have established this, it is known that every nucleus has a very unique pattern of gamma energy. This is an example of 78 TIFR. But it's like a fingerprint in the forensic science, that identifying the gamma energies which are emitted by a source or at the end of a reaction or whatever, one can identify which is the nucleus which is emitting the gamma. So this is called a level scheme, and it has a very special role to play in the future of this future slides. I'll go into history of what and how the gamma energies are measured. But in the latest of the advanced technologies that we have are the Clover detectors. This is, people are familiar with detectors for measuring gamma energy. We got scintillation detectors in the mid-60s, 1960s. Then around mid-80s, we got the jelly detectors, that is the germanium lithium detectors. Somewhere after that, about a decade, we got the high purity germanium detectors. And in somewhere around the change of century, around year 2000, we got the Clover detector, which is 5 times more efficient than HPG detector, but of course also very expensive. And hence, it is always required that a big array of gamma detectors is set up, because the way inherent interactions are, these detectors have very small photopeak efficiency. And hence in India, for example, in TIFR, I'm proud to say that we have an array of 24 such detectors. Of course, even with 24 such detectors, we only reach up to 5% of detection efficiency. But it is measurable and comparable to world's two other large arrays, the Gamma Sphere in USA and the Euroball, which is a European collaboration. And INGA, that is the Indian National Gamma Array, which has been active since year 2009 or so, is available in India, in Mumbai. Initially, it was rotating around India, between Delhi, Calcutta, and Mumbai, but now mainly it is stable at the TIFR Pelletron facility. So we see that if you want to study the nuclear structure, from theoretical side, an interaction between the neutrons is given by a model based upon the nuclear interactions. These models usually give us they predict the energy levels of a nucleus and the transition probability between them. This is the theoretical achievement. From the experimental side, also we can know the transition probabilities, but for which one needs experimentally the quantity called the gamma energy, that is a transition between two levels, the half-life of the level from where the energy is emitted, intensity of each of those transitions, and finally, of course, the levels, spin and parity information should be available. With these 4 informations, experimental information, one can achieve the transition probabilities and match it with theory to understand the nuclear models. Of course, if the match is very good, then it's very nice. If the match is not so good, then theoreticians keep playing with the different models to see which interaction is active in which region of the nuclear chart. It is not that a single model is available which will fit the whole nuclear chart. Okay, so when the nuclear numbers are close to magic numbers, it's a different model. When it's away from the magic numbers, we get a different model. So, but these different models have to be matched with the experimental technique. And hence, over the last many decades, all over the world, there is huge data which is published in terms of the nuclear decay, especially the gamma energies, the lifetimes, the transition, etc. But after joining HBCSE, there were different perspectives which came to understanding with talking to different colleagues there, and while we were dealing with education, the first and foremost question which came to mind was that what came first? In order to measure gamma energy, a detector has to be calibrated. And in order to calibrate a detector, we need to know the gamma energy. Okay, so what came first? and that's a chicken and egg story. It's a small history which I am trying to relate. And so the first attempt in this direction was in 1914, where if you look at the second line, what is now 214 lead or 214 bismuth, they were named very differently. Some radium chain B and radium decay chains. That time, people were not aware of these different nomenclatures that we know now. But one of these radium lines, which had actually 750 keV gamma transition, was first time measured in 1914 with a scattering phenomena from a crystal and measuring a wavelength of 70 milliangstroms, which was related to 177 keV. And then later on, in 1925, it got updated to 750. If we need more details, there is the most popular book in nuclear physics, which is the alpha beta gamma spectroscopy by Sigbaum, and you can see these details on page 208. Of course, then without going into much details of this history, it slowly developed into a more stronger resolving power instrument, and finally, in the mid 70s, we started getting more and more precise measurements. Just for the record, an old crystal diffraction spectrum from 1929 was then compared to a high resolution data from recent times, and you can see a very nice match between how these gamma energies were measured in the photographic plates as compared to spectrum from a germanium crystal. Okay, so what's next? We arrived at the history. We got the scintillation detectors with resolution of 7%, followed by HPG detectors with resolution of 0.2%, and so on. Lots of gamma ray information from hundreds of nuclei started coming in. And then a group of scientists started realizing a problem, that the same experiment conducted by 2 different groups or 4 different groups had data which did not match. Okay. A lot of this information from nuclear physics is used from outside the community by medical physics, industrial applications, the reactor technology groups, and various other, and finally the research group community, which needs a single answer to any given single measurement. But if there are 5 different, how does one account for the question, what is the answer or what is the value of a particular measurement? And problem is not as simple as I just mentioned. I will give some examples. Is there a single level scheme for any given nucleus? Okay, so on. And hence came out the data by scientists from European and the Brookhaven collaboration. And it was called the Nuclear Data Evaluation Group. It was funded by IAEA. And people from all over the world started pitching into this program. The purpose and philosophy was to present the best data available from each type of experiment, to present the best information for each nuclei as a result of this evaluation, to present concise, consistent, and well-documented information of all the experimental data from nuclei. For example, here, I'm just quoting an example of 223 thorium. You can see that there are 2 different level schemes of thorium, okay, depending on which experiment you do. So for example, on the left, you have 227 union in alpha decay, which only populates these 5 levels. Whereas if you had a nuclear reaction of oxygen beam on lead target, you get a completely different set of levels, barring the bottom two. Okay. And this is the simplest of the case. So you can see only 51.3 keV level is common. The rest of the levels are not. As a scientist, for research scientist, if one was to study or interested in studying 223 thorium, it may not be possible that it's possible that the researcher can completely miss one of these level states. And hence, of course, the situation is more complicated in many other nuclei where people can do 15 different kind of experiments and can have 12 different kind of level schemes which they match completely or partially or none at all. Okay, so the data evaluation program, which started in early 1930s, was to standardize the experimental data. Okay, combine all these experiments, all this information from different experiments and publish the data. Okay, there are either discrepancies in the published data. It should be settled, issues should be settled between different experiments and within the same experiment, and put the standardized data available in an easy format which is accessible to all. Of course, this is not a clerical job. It requires the experience of years of experiments or even sometimes theoretical experience. And then it has trying to solve the issues has sometimes led to new experiments or even new direction to research in nuclear physics. So published experimental data needs to be compiled into one single set, collect all the experimental level schemes and other information connected with those levels and gamma energies into a set called as adopted set. So let me give again a brief history of this project. It started in 1931 with the publication of the first paper of this in this project, in Review of Modern Physics, and all it had was half-lives of the about 13 odd nuclei in the heavy mass region. Okay. So you can see column number 2 is half-life, its related decay constants, and if there was any gamma energy related information. And last column was about the references where this information can be available. The next came in 1939 with a similar data on low mass region. Okay. So it's only all about hydrogen, helium, carbon, nitrogen. This continued till about 1958, where such compilations were published every 4 years. And finally, after 1958, a new set of research journal called Nuclear Data Sheets. These are yellow colored books which will be available in many of the libraries, was an end result of this program called the data evaluation. And now, of course, it has become a very voluminous publication on different mass chains. Just one more example of 1937 publication from where it started. So now let me switch the track from the history to some of the experiences of this project in which I have been working. And there are about 4 or 5 faculty members in India from all over India who are collaborating on this project. And we are always on the lookout for new people to join us, whether it's faculty or student members who are interested in this kind of work. So about a few years ago, I was looking after the mass 139, where there were about 16 nuclei which were evaluated, all 139 SB tellurium to disposal. In 139, the interesting thing was that in 139 barium, we had lot of discrepancies in the measurement of half-lives, which led to eventually to doing an experiment at DRC by ourselves to solve the issue. What was the problem? The problem was that in the history of nuclear experimental physics, there were 13 measurements. And as you can see, that 8 of them fall very close to each other in giving one average value. The other group of experiments gave another set of values, and there were 5 of them. In fact, I have not included here in the text, but the 5 were more precise measurements, but had very little data. These 8 had large amount of data, but with poor precision. So it was really difficult to give a standard answer for what is the half-life of 139 barium. Here, I have tried to show that if we took unweighted mean of 2 groups separately, they fall way apart. And if you took unweighted mean of the complete 13 experiment, it falls somewhere in the middle. So nothing talks to each other. Same is the case with weighted average, and there are some other techniques which are used to solve the issue, but none of them work. The weighted average for one group is 83.0 with an error of 0.16 minutes. The other group is 84.55 with an error of 0.2 minutes. And incidentally, this nucleus is also very widely used in medical research. So this was a critical nucleus to be handled. Okay. So in order to solve the issue, we eventually landed up doing an experiment ourselves. And the answer was matching with one group, okay, which had large data but less precision. Okay, which had more precision but less small amount of data, the second group. And so finally, now this is the answer to the question, what is the half-life of 139 barium? So there were some other additional advantages of this experiment, which I'm not discussing. Let me discuss some more observations from data evaluation, especially in Indian context. The challenges that come from published papers. Now, what we are talking here is data which is published in reputed journals and still has problems. How can we avoid this? So this is the first example. I specifically purposely removed the reference to which nucleus it is because it can reveal the name of the author, so that's not my intention. But in this case, you can see that the existing data had some level, some gamma transitions in one band, some other gammas in some other band, of course in the same nuclei. But in the new publication, they were all lined up in one single band. And there was no physics explanation as to why there is so much change that is being proposed, or actually even a confirmation or some kind of word to prove that the old data is not valid anymore or anything like that. Now, as a reader, as a researcher who wants to study this nuclei, it would be a problem to understand which one is the correct level scheme of this nucleus. And hence this was one of the toughest problems where we had to contact the authors and eventually with a collaborative effort, we could solve the issue to find out how to give the compact data final answer. Because both experiments were same target, same reaction, same quantity of data, same kind of detectors, and there was practically nothing that could tip the balance towards one of the experiments. So in the same case, same nucleus, there was also another problem like this where in a level scheme, this gamma energy is completely missing. Okay. And this actually makes it very difficult because all the spins and parities, of course, above it get disturbed. Another problem we found, and this is particularly, which was an Indian paper, that what you see here in a level scheme where the thickness of the transition depicts the intensity. And so far, everything looks very good. But when one looked at the table of the data, one finds that this energy here has a very low intensity. Now, if in between suddenly the intensity drops from 97 to 75, where did the intensity go? There is hardly any example in the nature where from a level scheme, from somewhere in the middle of the level scheme, a transition goes to out to another nuclei and has not been seen or not detected. Okay, if one assumes only gamma energy, there could be a problem. So let's add the conversion electrons to it, and the problem gets reversed. That this transition had much higher intensity than the ones below it. And of course, the authors had not made any attempt to highlight this problem. And unfortunately, that's still an unsolved problem which we are working on. We don't know how to solve the problem because authors need to explain how this paper was published with mismatch like this. Again, similar problems which we see quite often is this, that the 212 kV transition has much lower intensity than the two which feed it from above. And no answer. This is an example which particularly would like to highlight to students who are listening to me that they should never do a mistake like this, that when they highlight the gamma energies, they have put, this authors had put only integral numbers. Now, it is impossible to say that every digit after decimal in every transition was zero. It's highly unlikely. And with the advanced detectors that I highlighted in the beginning, which was with this purpose, where resolution is very, very nice and very fine. And these days, the gamma energies with 2 digits after decimal are also possible. Whereas this publication talks only about integral numbers. There are also problems that the numbers in the table did not match with the numbers in the text explaining the gamma ray or even the levels. So as a reader, one does not know which number to believe. Is it the level scheme, is it the table, or is it the text? So within their own paper, people had published data which had inconsistent numbers. And as evaluators, we find it very difficult to solve such issues. Sometimes we can approach the authors. If they give us information privately, we use it. Otherwise, we have to go case by case how to solve the problem. So how do we... So all these issues, which are of course not only problems, but we have to kind of mix them, are converted into this one single data called the NSTEF format. This NSTEF stands for the Evaluated Nucleus Structure Data Format. And I will come to some of the codes, how they help in solving such issues. There's one more problem which, while doing this evaluation, we encountered. That, as I said in the beginning, that half-life is the most important quantity to be measured, besides the gamma energy. But is the nuclear community measuring such half-lives in such large numbers? Okay. And so, initially, just as a query, what I did was I took the same 139 nucleus which I was studying, And here are the elements listed. The third column tells how many number of quantum levels have been observed or measured in each nuclei. So for example, if I take 57 Z139 lanthanum, there are 308 levels which have been measured experimentally. So their levels, the gamma transitions from them have all been observed. But only 5 levels have the half-lives measured. 5 out of 308. The same is the story with spin and parity, very small numbers. If you look at 139 cerium, 106 levels are observed, only 16 half-lives are measured. So the discussion was it that 139 was a particular problem or is it a generic one? So I just randomly took one other mass chain, which is mass 188. And the same is the story here, that 188 rhenium has 81 levels, only 13 half-lives. Or iridium has, platinum has 73 levels and only 4 half-lives. Now, if half-life is such an important quantity, why is it not measured so much? Or is it? How do we know? So we decided to conduct a survey over whole nuclear chart of 3,300 nuclei and define a p-value. It's very simple. It's actually a probability number. That number of levels whose half-lives are measured divided by total number of levels observed into 100. So for example, if a nuclei has 137 energy levels, and if only 17 of them have the half-lives measured, then p-value is defined by 17 divided by 137 into 100. Of course, if there are very few levels, so for example, if there is a level scheme with only 5 levels, the p-values can only be discrete, 20, 40, 60, 80, or 100. But where there are large number of levels known, this p can be it can have more decimal numbers. Of course, to cut the story short, we picked up all the 3,300 nuclei, eliminated some which have no level information, some which exist at the end of the edge of the chart and are very difficult to produce in experiments and things like that. And we kind of narrowed down to the search to 2,220 nuclei in the nuclear chart and to see how the p-values are standing. And this is the distribution of those 2,220 p-values which are measured. And it turns out that the median is only at 11%, which means that for 50% of the nuclei, less than 11% of their level lifetimes have been measured. In spite of being such an important quantity, it is very scarcely measured. In fact, the peak is only at 4%. Okay, I'll skip more details into it, that there are many nuclei with absolutely no half-life measured. Okay. And there are 403 nuclei where only the ground state half-life is known, nothing about it, even though they may have many excited levels. Same is the story with spin and parity. 485 nuclei with practically no spin and parity information available. If it's available, it is tentative based on some theoretical predictions and models and things like that, but no experimental measurements. So we started a search engine, okay, which is of course now available for everybody to see, where if you simply type in the mass number, okay, you can immediately get these p-values. So for example, if you take mass number 176, it tells you that for lutetium, there are 164 levels available and 18 half-lives have been measured, so on. This paper was, on this chart was published in May 2020 in India. So data evaluation has led to a new measurements, refinement of data, better understanding of how the research is proceeding, and has led to even new experiments, and has just helped making nuclear physics richer. I'll just spend last 5 minutes on how we do it. So in order to do the data evaluation, we have a particular format in which the data is collated. I will just come to it. But then one can run computer codes which give you the conversion coefficients of each transition. Which is, of course, very much, over the years, it has evolved into a very rigid program so that it gives robust values better than even experiments. There is another code which helps you indicate if there are mismatch between intensities, between gamma energies, typing errors. Okay, it will pick out all the numbers which mismatch. So if students who are interested in nuclear physics, if they just understand this format, which probably takes few hours to understand, and run this code, a lot of the problems which are identified in my previous slides could be tackled before publication. There are codes which will find out physics errors like inconsistent spins and parities, okay, inconsistencies between branching ratios and things like that. So this, as I said, this was a group of several nuclear physics communities which started all over the world. Currently, it's headed by IAEA-Data section, and there are 13 data evaluation centers around the world, where India is one of them. There are lots of people in BRC who work on other aspects of nuclear physics, but on this side of nuclear structure, there are about 4 or 5 faculty, as I said in the beginning. This NSTEP format file, it has a data where it talks about the source from where the data is coming. It has been the source for table of isotopes. So those people who have been seen in the olden days, very thick volumes consisting of nuclear data called the table of isotopes. That used to be the output or the product of this NSTEP format. Of course, now it has become online. Nuclear data sheets are the journals which come from this format. Okay. And there are many small booklets which have come out, which are very handy to people who are working in nuclear physics. They're all outputs of this evaluation program. And of course, most of it is now online. Now, I will not bother you with the details, but the format talks about the history of the file, when it was evaluated, what are the experiments, okay, general comments about that nuclei, where does it decay from, which kind of decays produce this nuclei, their level information, gamma information, and all this is included in one single location. Let me run through this. I'll just give you an example how, for example, in case of 139 tellurium, it would define which experiment it was studied in. Its reference in publications are through these shortcuts, which are very easy to note, but they are easily available. When you click on them, it gives you the publication. And then there are various other information, which is just highlighting the kind of information. You doesn't have to look at all of them, but the amount of information that is put into this file. Okay. Okay. So here, so it talks about the placements in the level scheme. It talks about the intensities, partial intensities, multipolarities, mixing ratios, all the information which one needs to know about any particular nucleus is compiled in this file, which is from NNBC. This is just an example of how the file is written in the text format and how it is converted into a very user-friendly approach in a PDF version. This is just one page of it, but it talks about all the information compiled in a very highly readable format for researchers who are not involved in research project. Where do we get? Where is the starting point for this? Okay, there is one site from Brookhaven where if one clicks on any of these options, you get the information based on the publication menu. This is from the mass number information, etc. So all you need to do is if you type in the mass number or any nuclei, one can get these levels, one can select to see whatever you want. These are the individual experiments or the compiled data. This is the text format that I was talking about. Of course, this is a very, very long file and converted into a very user-friendly, readable form. So, for example, 180 hafnium, and right in the beginning, it talks about who are the people who evaluated it, which experiments led to the information on these experiments. All the possible experimental measurements which have been published so far are given in the comment section. The discrepancies are also listed here. So a researcher or an applicator, application-based person, medical physics people, can actually get all that they require from this one single file. So in summary, I think I'm just about to finish in time. It helps us standardize the values of the published data. They're not before publication. It identifies mismatches between published experiment data, resolve them for the scientific community, shows how to resolve the inconsistencies in any given data. It has shown directions for new research. For example, the survey on the p-values. It has become a useful tool for researchers to come and see which are the regions where half-lives have not been measured or they have been measured, spin parity information is missing, things like that. It has also given us opportunity to plan new experiments. Okay, so it always keeps on making the information more and more resolved and finer. And many other aspects of this. So, this survey of the half-lives is available on the TIFR webpage for people to see. The evaluated data the source of all our data is from the Brookhaven site, and it is all in the HDEF format. If anyone is interested in this kind of project to join us, you can contact me here at what of you know. And such a large program cannot be done singly. So we have to acknowledge the MSc student from Soumya College who was the first student to do the survey. We also involved the Olympiad students. So one of the gold medalists from IJSO was involved in writing the computer codes when he was a student at IIT Bombay. We had other 3 students who have been updating the information ever since this survey was started. It gets updated every 6 months to a year. And there are 3 faculty members currently who have listed. I actually missed one person from Bombay University who has just joined us. So with that, this is the program about the nuclear data evaluation, published experimental data. Thank you very much.
Thank you, sir. Are there any questions? The platform is open for your questions now. Yes, anyone with any question?
To ask one question, I'm trying to go on to here. Paresh, you mentioned you carried out some experiments to evaluate the data, and then your answer failed in one of the groups. So was your experimental method, why was was it better, or was there anything in the method that said that is a better value?
Yes. Okay. In the two groups of data, the one group had large amount of data, but they were not very precise measurements. So what happens is that in measuring lifetime, there are different techniques that can be used. Okay. And with the kind of detectors available and with the experimental information that is usually given in the published data, we could see that this group had large data, but they had very imprecise measurement techniques. The other group had very precise measurements, but very small amount of data. What I mean is that if the half-life is 10 minutes, and if you collect your sample only for 3 minutes, that's not appropriate, because then your error bars are large. And actually people had done, I would say, not mistakes, but they had actually done things like that. Okay, that if you have half-life of 10 minutes, you should collect the data for at least 40 minutes to give you the lifetime with some confidence. So this is what we did. We had the opportunity to have the best detectors to be used, and we planned it for collecting the data for more than 5 or 6 half-lives. Over and above that, we had the advantage of this Clover detector. So we could do something which nobody else had done earlier, to filter the data much better than the previous groups. So with that kind of experimental technology available, our number was preferred over all others. I mean, that's why it supported the one group of numbers, and so we took weighted average. We did not ignore the other numbers, but our weightage was very high, and other numbers were also included to give a final number.
Any other question?
Yeah, third question.
Yes.
So suppose, I mean, this is not directly related to your experiment, but generally we, a common physics student is not aware, or even many times we are not aware of the methods by which the half-life of very long-living parent is measured. One method we can think of is a long-living parent may have a daughter element which is short-living, and then you know that there is an equilibrium, and therefore the activities must be same. And if I can measure the half-life of the daughter, then I will be able to calculate. Now, has it occurred that because you change or you measured more precisely the daughter element, and therefore you have to change the very long-living half-life of parent? Such kind of modification changes, has it occurred to your experiments?
This was only one experiment which we did in measurement of half-life. We did not look at the relative other two half-lives. But what happens is that since we were just confirming one of the two groups, okay, and the variation was not so high, it actually does not affect the other half-lives. But I'm not saying it's not possible, it's possible. But what happens is that when the upper or the next decay nuclei is being studied by some evaluation group, they will pick it up, okay, and they will see if this is impacting them or not, and they will do the needful. So if required, they may even do another measurement. So usually when you go from one nuclei, somebody else will look at the other nuclei which this half-life is affecting, they will pick up the issue.
Thank you, sir. So this means probably this entire method can be applied to many new nuclides, and the lot of data could be precisely measured or revived.
Yeah, usually one does not go for every imprecise measurement. Okay. In this particular case, because we had a discrepancy, we had to do the experiment. But yes, there are, if one nuclear group identifies that the half-life has been measured with lot of imprecision or large error bars, and for some physics reason they want to improve the error bars of those measurements, people do such experiments.
Thank you, sir.
Yes, any other question? No one has any other question?
There is one question in the
Yes.
chat box.
Yeah, in the chat it is asked, sir, is there any opportunity for college teacher to do research in TIFR?
You mean physics research or education research?
Yes, sir, physics teacher.
Sorry, sir, we are not able to hear you. If you can type the thing, it will be better. Akhtar, sir, we are not able to hear you.
Yeah, physics research. Okay. Yeah, see, there is always a possibility, and what you can do is, okay, in nuclear physics, yes, what you can do is that you can approach the group, okay, which is working in field if you're of your interest, whether it's nuclear physics or any other physics. And if you have the time and you can contribute, it's certainly possible to join the groups. That's not a no. Okay, it's always possible. All you have to do is you have to identify the project in which you want to work, and you can approach us. And there are many teachers who join as university teachers and things like that. And in nuclear physics, there is a center at Calcutta called the UGC DAE facility. The name has recently changed, and I don't know the new name, but only the name has changed. Their whole agenda, the purpose of that center is to liaison between UGC facilities, which are colleges and universities, and the DAE centers like BRC, TIFR, VCC. We can also approach them. They even give funding for college teachers or university teachers to conduct research if they want to, if they have any project in mind. Okay, not student project, but research projects. So that's another opportunity, and then you can actually go and do the experiments at the Inter-University Accelerator Facility at Delhi. You need not worry about TIFR. So that route is also open for teachers.
Thank you, sir. Any other question? Okay, so I will now invite Dr. Kiran Kolvankar for the pleasant job of vote of thanks on behalf of IIPT Mumbai Sub-Regional Council. Kiran, sir.
Yes, thank you, Shamra Madam. It's really my pleasant duty to present this vote of thanks. First and foremost, I would thank the speaker, Dr. Paresh Joshi, for taking time out and giving such a nice, lucid and clear talk. Then I would also like to thank Professor Dr. Pradhan and Professor Oglapurkar for being present here and gracing the occasion. Also, Professor Aluwalia, thanks to you too for being here. Then I would like to thank Principal of Xavier's College for making this Zoom platform available to us, and Dr. Leena Joshi Madam for taking care of creating the link and making YouTube live. And of course, all the audience for your active participation. I thank you all, and we'll continue this in future too. Thank you all.
Thank you. Thank you, everyone.